Hi everyone, I'm Steven Holtzen. This talk is called Scaling Exact Inference for Discrete Probabilistic Programs. This is work that I did at UCLA with Guy and Todd. So first I'm going to give a high-level overview of what probabilistic programming is. In short, probabilistic programming uses programming languages to create probabilistic models. So here we have an example of a programming language. We see that first we flip a coin, this flip 1, 0.1, which returns true with probability 0.1. That's what makes this program a probabilistic program. Then y looks at the variable x. This is standard program syntax. And if x is true, then it flips one coin. Otherwise, it flips a different coin. Similarly, z then looks at y. And if y is true, you flip one coin. Otherwise, you flip another coin. Here, all these flips have subscripts. This is just for discussion. They don't have any meaning for the program. So our goal in a probabilistic program is to perform probabilistic inference. In particular, we want to compute the probability that this program returns true, where z is the return value. And we can see an example of probabilistic inference over here, where we've computed that this program returns true with probability 0.47 and false with probability 0.53. Programming languages make specifying probability models natural, which is one of the big advantages of probabilistic programs. They're composable and reusable, etc. Probabilistic modeling is widely useful. It's been used in text analysis in order to decrypt text. We'll see an example of this later. It's been used in probabilistic network verification. It's been used in seismic monitoring, medical diagnosis, and there's a host of other applications in these textbooks. But universally, the most challenging problem in deploying probabilistic programs and probabilistic models in general is scaling inference, which is the problem that DICE is going to tackle. DICE is a new probabilistic programming language that focuses on finite discrete random variables. It supports bounded integers, first-class observations, functions, bounded iteration. And it does modular function analysis, which amortizes the cost of doing inference if you have repeated function calls. The design of DICE balances restrictions on the language. For instance, we do not support unbounded loops in DICE, with expressivity to allow one to define interesting probabilistic models. And the reason we restrict the language is so that we can design new and interesting inference algorithms. In particular, DICE's inference algorithm scales to hundreds of thousands of discrete random variables in extremely large programs. We formally prove this inference algorithm correct with respect to a denotational semantics. And if you want, you can check out this website, dicelang.cs.ucla.edu, which has a link to the paper, a live demo you can play with, and more information, including a GitHub repo for the source code. So I'm going to talk a little bit about DICE and how it works, but first I'm going to talk through a motivating example. So in this example, we're going to decrypt some text using a Caesar cipher. Caesar cipher is a well-known encryption algorithm where you simply map one character to another in the English alphabet by shifting. Cracking a Caesar cipher can be cast as probabilistic inference using something called frequency analysis. So we assume that each letter is drawn for a well-known distribution on English letters. I have such a distribution down here in the lower left. For instance, we can see that the letter E is the most likely character in the English language. We're going to observe the ciphertext using Bayesian conditioning and compute a posterior probability on the key. So this seems like a natural program. We can write a program that draws a character from this probability distribution here and encrypts it, and then we can observe that it takes on the observed ciphertext. So let's make this program and see what it does, and then use probabilistic inference in order to decrypt. So in this case, our observed ciphertext is TVSK. So I'm going to move backwards and forwards between letters and integers here in this discussion. So the first thing we're going to do is look inside this encrypt character function. And it takes two arguments, a key and the ciphertext. So the ciphertext is going to be what we observe. So first we're going to draw a character from this empirical distribution on English letters. Then we're going to encrypt that character by shifting it around. We add the key to it, and then we take mod 26. And we're going to observe that the ciphertext is going to equal this encrypted character that we drew. Then we're in the main body. This is the main body of the function. The first thing we're going to do is draw a uniform key. So to do that, we choose an integer between 0 and 25, or a letter between 0 and 25, between A and Z. And this is uniform prior, because we're not going to assume that any particular key is any more likely than any other key. And in the end, we return a posterior distribution on the key on these numbers or equivalently on those letters. Now notice, this program only describes how to draw a sample. The probabilistic inference task is going to be to take this forward model that tells us how to draw a sample and compute the distribution after you've observed this ciphertext. So let's see how to do that. But first, I want to give a high-level kind of punchline. So dice is going to scale extremely well in this particular example. So we can see that for this example, dice can scale to on the order of 10,000 characters. And some other probabilistic program inference algorithms, such as Psi and WebPeople, two well-known exact probabilistic inference algorithms, can struggle with certain parts of this problem. And we'll go into more detail why later in the slides and in the paper. First, I want to talk about rejection sampling. So rejection sampling is a well-known approximate probabilistic inference algorithm, and it's a special case of many existing sampling algorithms. And the way it works is as follows. When we're running the program, we get to this uniform int. And the first thing we do is we draw a sample from it. So we choose 8. Notice here I've replaced letters with numbers just for convenience. Then I'm going to call encrypt_char. I'm going to go inside this encrypt character function, and I'm going to choose a character from my empirical distribution on the English letters. So it could be A, B, E, or whatever, and I choose E, or number 4. Then I'm going to encrypt it by adding 4 and 8 together, the key with the random character that I drew, mod 26, which will give me 12. And here's the important part. Then I observe that this sampled ciphertext is going to be equal to the original ciphertext that I want to decrypt. And this isn't the case, because 12 does not equal 25. 12 does not equal 20. So we discard the sample, we throw it away, and we have to try again. And we have to keep sampling until we get one that does satisfy this condition. So this is going to be why rejection sampling scales poorly for this particular problem. We'll need to draw many, many characters before we get ones that satisfy this observation for all the characters we see. And we can see that even after 5 characters, the time's growing very fast. Moreover, this problem is non-differentiable. It causes problems for many sampling algorithms, for instance, Hamiltonian Monte Carlo, that rely on differentiating the program in order to perform probabilistic inference. So let's look at another direction. Let's talk about exact inference algorithms. In this case, we'll talk about path enumeration, which is a well-known method for doing probabilistic inference on probabilistic programs, and it's quite simple. The way it works is you branch on every possible value of every variable in the program. So I'll start here with the key, and I branch on every possible value it can take. Then I go inside encrypt character, and I look at the random character function, and I draw a sample from every possible value it can take, and so on. Now clearly this scales exponentially, and we can see that at around 16 characters, this starts to blow up. So how does dice work? How does dice avoid this explosion and scale to tens or even hundreds of thousands of characters on this particular example? So let's go back to inference by enumeration. We just saw it. We're going to draw it a little bit differently now. We're going to draw it as a tree. So on this particular program here, back to our motivating example, we're going to branch on every possible value the flip can take. So I'm going to label the outcome of flip 1 as F1. So if flip 1 is true, then I have to flip coin 2. So I flip F2. If that comes up true, then I flip coin 4. And if all these coins come up true, then I return true. This tells me the return value of the program. Otherwise, I return false. And so on, I can fill in this tree. And from this tree, I can read off terms in a polynomial that tells me how I can compute the final probability of this being true. So here I see that if I take this path here, that winds up being returning true, I can compute its probability by taking a simple product of the probability of each of these flipped assignments coming from the program, 0.2 times 0.1 times 0.4. So I sum up all the ways the program can return true, and then I can do my inference algorithm on this program. But observe, there are some redundancies here. X's value doesn't directly affect Z. And we can see that because these two leaves are identical, and similarly these two leaves. And this shows up in the sum. We can see this 0.1 it shows up twice. And this sort of structure, where we have this repetitious repeating of leaves along different branches, also occurs in the encrypt character example, which is going to be why we scale so well on that example. So dice exploits this kind of redundancy, and it does so by factorizing inference. We can write this exploration more efficiently by sharing structure and knowing that z's value doesn't depend directly on x. So we can draw the same tree we drew before, but now we can share these leaves between these two different branches of F2 and F3. And this reduces the size of that exploration tree that we had earlier. And it lets us write a much more compact representation of the sum. And in general, by saving these terms, by collapsing this tree and sharing structure, we can perform inference exponentially faster than if we were doing it the naive way. And it's directly exploiting program structure. It's exploiting the fact that z is independent of x given y. This is one example of structure that dice can exploit, but it isn't the only one. So how can we generate this compact state space representation without exhaustively enumerating, without exploring all possible assignments, and then collapsing the tree? How can we do this? So here's how dice does it. So we start with a dice program, and we run it through the dice compiler. And it produces a binary decision diagram, which is a representation of the state space of the program that automatically caches and reuses repetitious structure in the program. Once we get this binary decision diagram, and note, there are no probabilities in this data structure. It's a purely logical data structure. Next, we introduce the probabilities here. This process is called weighted model counting, and it's a well-known process that's currently one of the state-of-the-art methods in discrete probabilistic graphical models and in probabilistic logic program inference. So then we incorporate the probabilities into this data structure and do a single pass over this binary decision diagram in order to get our inference result. In order to generate this binary decision diagram, we compile the programs modularly. We compile each subprogram into a binary decision diagram, which is then combined to produce a larger binary decision diagram all the way up through the program. This means that we can compile functions modularly. We compile it to a binary decision diagram once, and then we reuse it for all subsequent calls. And in the paper, we show that this gives us an order of magnitude speedup over the naive approach of inlining the functions. In particular, on this encrypt character example, we see a significant improvement because you can avoid recompiling the function many times for each call. So let's see an example of an experiment that highlights how effective this compilation weighted model counting strategy is. There are some more experiments in the paper. So we talk about some common baselines that are well known throughout the literature. In particular, we take all of the discrete benchmarks from Psi and compare against it. And we also show some scaling experiments on network reachability and some variants of the Caesar cipher example that we showed earlier that are more challenging and interesting. So check out the paper for those. But here I want to highlight one particularly compelling, in our opinion, probabilistic inference task, which is exact marginal inference for Bayesian networks. So Bayesian networks, they're historic. There are tons of examples of interesting Bayesian networks. We chose several challenging discrete Bayesian networks and turned them into probabilistic programs. We translated them into dice and we translated them into Psi. And then we compared the performance on these realistic and challenging models. Some of these models have tens of thousands of variables in them and are extremely challenging for existing probabilistic programming systems. So here we see and can compare the performance. We see that Psi has two inference algorithms that we compare against. Their symbolic inference algorithm and their dynamic programming inference algorithm, which is specialized for discrete probabilistic programs. So we see that on these medium to small sized Bayesian networks, such as Cancer and Survey, Psi can perform exact inference on this particular marginal query. Dice is faster, but these numbers are relatively small. However, as we get to the larger Bayesian networks, some of these are extremely large. For instance, Munin has over 100,000 random variables in it. We can see that dice still takes around a second. And one way to really see the savings of dice is to compare the number of paths. That if you were doing a naive exact enumeration, this is how many paths you would have to take to explore the entire program, against the final size of the BDD that gets generated. And we can see that that dice has an enormous savings here by generating a relatively small BDD that represents a truly enormous number of paths. So to conclude and to talk about some future work briefly, we presented a new exact inference algorithm for probabilistic programming languages based on weighted model counting binary decision diagram compilation. It's fast and proven correct. And in the future, we think it would be compelling to look at hybrid models and to add more expressive language features to dice, for instance, to handle arbitrary non-terminating loops. And with that, I'll take your questions. Thank you very much for your attention.